Okay. I think last time we did leave off on that example I was trying to make about when you multiply things together. So I want to make that a little more specific. Again, I think nobody really fessed up that they didn't really understand cards too well, so I'm going to come back to cards because it's just so perfect for probability practice. So somebody remind me, what's the probability I pick a king?
1 out of 13.
Good. So there's 4 out of 52, which reduces to 1 out of 13. Remind me, where did that 52 come from? That's because there's...
52 cards.
Good. So the bottom is always the total number of things it could be. And the top is always the total number of things that match what you're looking for. You have 4 chances out of 52 to get what you want. So it's like the lottery. It's nearly impossible to win because you only have 1 chance out of 7 million or whatever, right? But we still try. What the hell? So this is picking 1 card. Now let's move on. What if I pick 2 cards? How is that going to work? It's going to be a lot like that idea of getting hit in the one cheek was a 1/5 probability every 5 steps, bam, right? And every 9 steps, bam, a 1/9 probability. And what did we do? We ended up multiplying, didn't we? Mm-hmm. How many steps on 1 out of how many steps would I get hit in both? 1 out of 45. I just multiply the probabilities together. So to pick 2 cards, what's probably I pick a king and then another king. Now, before we even do the math, what makes sense here? How should this probability relate to that one? Which one should be less likely to do? Obviously, the second one, right? It's hard enough to pick a king at random. You're like, I want a king. Bam, I got it. Oh, my God. And like, oh, let me get greedy. Let me get another king. You know, it's like, holy crap, just be happy you got the one king. It's going to be really hard to just randomly pick another king on the heels of that one, right? So I have to be a little specific on how I'm doing this, though. Let's say I'm doing this with replacement. So we're slowly approaching your question from earlier. We're not quite there yet. Because how many ways is there to pick a card? Can't I pick a card and then put it back? Mm-hmm. Almost like it's going to be a magic trick, which I can't do any, so don't get... I won't bore you with the magic tricks, thank God. What's the probability to get that first king by itself?
1 out of 13.
1 out of 13, or 4 out of 52. Now I put that king back in. What's the probability I get another king on the next go-around? Still 4 out of 52, right? So I always think of it like a hangman game. If I have 2 things I'm doing, there's 2 spots to fill with a probability. And then I'm going to multiply them together because I want to do the first one and the second one. And basically means multiply. And then you get 1/13 times 1/13, 1 over 169. You can make it into a decimal, right? Cool. Whatever the hell that is as a decimal. I have no idea. All right, let me try one more. What's the probability you get an ace and then a club? And you're still picking it with replacement. You're putting it back in, right? So it's probably get that first card. So I got like these 2 blank spots because I got 2 things I'm doing. I'm picking 2 cards. What's probably that first card is an ace?
4 out of 52.
Exactly. 4 out of 52 because there's 4 of every card, right? Put that ace back in. Now what's the chances I pick a club next?
13 out of 52.
I love it because there's 13 of each suit, right, to make 52 total. So it'll be times 13 out of 52. And that becomes actually 1/13 times 13 over 52. 13's cancel. You can have to do all this in your calculator. That'd be roughly just under 2% chance.
Okay, explain that one to me one more time.
So what's the probability you get an ace on the first pick?
4.
Okay, now you put that back in. And thankfully you put it back in because the ace could have been a club, which would freak out the second part of this, wouldn't it? So I put that back in. Now how many clubs are in the deck? What's probably get a club now?
13 of them.
13?
13, yeah.
So times 13 out of 52 because this is an and problem, right? Now do you have a problem with just the math I did? Is that
No.
But
No.
that's-
That's the part I wanted to understand.
I got you. So that's how that works.
Okay.
It's really cool. It's kind of like two separate probability problems, and since it's an and, you multiply them together. And I really, why does somebody put multiple locks on a door if you
Oh.
live in certain neighborhoods or just if
Crazy,
you...
like in New York.
You're not, yeah, not necessarily the person's crazy with the door, but the people are crazy outside the door, right? So you want to put multiple locks. Why? There's a certain chance they'll get through one lock,
Then you have to do it again.
and then they have to do it again. So it would really suck if and was add. If there's a 1% chance they get through one lock, and I've got 10 locks up there, if I added them together, it'd be 1 plus 1 plus 1. Now they got a 10% chance to get in. They got a better chance. That didn't make a damn bit of sense. So if I have 2 locks on a door, here's my door, and I got a lock, and I got some other type of lock. So it's a chain lock. Let's say there's a 1% chance to get through this, and a 1% chance to get through that. So 1% of the time, they'll get through that top one. 1% of those times, they'll get through the bottom lock also. So what did I just say? It's a 1% of 1% of the time. And who remembers what of means with percentages? Nobody ever does, but of means multiply, right? 1% of 1%. So 0.01 times 0.01. So this is really what's going on. This percentage of the time I'll get an ace first. And that percentage of this percentage of the time I'll get both. Of means multiply. So there's several reasons why. There's a cheek clapping reason, and there's more of a straight up mathematical reason. You're seeing percentage of percentage, multiply. Okay, cool. So here finally is the question you asked earlier. Elaine. If I do this without replacement, meaning I don't put the card back in. I feed it to my little brother, I throw it away, whatever, right? So if I got, let's see, 4. If I do it without replacement, what's probably get a king, and then let's say an 8. So there's still 2 spots to fill here, right? 2 things I'm doing. What's the probability of the first thing happening? 4 to 52. Now I throw that card away, right? What's the probability of the next thing happening then? What's going to be at the bottom of the next thing? 51, because I just threw a card away. Ah. So the bottom is always the total number of things it could be. Well, if you threw one of them away, it's one less thing it could be, right? And how many 8s are still in the deck? 4. Because you didn't throw an 8 away, you threw a king away, right? And now you multiply that and see what the hell happens. Right. 113 times 40, whatever that is. Give me that. What's that as a decimal? Somebody help me out there. What's that?
What is it?
4 divided by 52 times 4 divided by 51.
0.006.
0.006? Is that what you guys are getting? Which is actually, what is a percent? I love it. 0.6%. 0.6% chance of randomly getting a king, throwing it away, and then getting an 8. So if somebody did that consistently, that would be a pretty good magic trick. It'd be actually pretty boring, but now you guys realize the probability of that's crazy small. That you get a king, throw it away, and then you get an 8. That's a really small probability of that just randomly happening, right? Okay. So here's the ultimate thing on this. Let's probably get a king and then another king. I think you guys might see what's going to happen here. So the first king, nothing's happened yet. He's still 4 to 52. Now how many cards are there? And how many kings are there?
3.
Good, because you're saying the probability you got a king. So this is how many chances it could be a king. In those times you would throw a king away. So there's one less king, one less card. Do you guys see how those go together? Okay, some of you guys might. All right, good. And then whatever that is. Is it 0.45%? 0045. Did I do that in my head right? All right, sweet. 0.45%. Yay, I do math. All right. All right. So just to give you guys an idea of what it's going to look like in the book, because sometimes their problems are a little different than what we're used to. So I don't think they've talked about. So here's a good example. Let's say the probability of left-hander, I think in this class it was higher. It's like 15% or something like that. Let's say it's 15%. So I want to pick 3 people. What's the probability that all 3 are left-handed? Now, if I have a large population, let's say this is out of the entire United States, right? This is a very large population. How much would this really change? If it's like, so many out of 310 million, and then the next one would be so many divided by 309,999,999. Will that really change that much? I mean, 4 out of 52 is actually a lot different from 3 out of 51. They are very different. If you do them in your calculator, you will actually come out with a decently big difference. But what is 100 divided by that, or 99 divided by 1 less than that? Those are going to be basically the same. So the really cool thing with large populations, I don't have to worry about changing this number. The mistake I see people make is they'll do this, 15 out of 100 times 14 out of 99. Now, what's the mistake there? How many people are they saying is in the U.S.?
100.
100 people in the U.S. That, of course, is crazy. Right? There's a few more people. That's no good. All I have to do here is, and again, I love the idea of the hangman game. It makes it a lot easier. I've got 3 spots here to fill, right? The first one I want to be left-handed. What's probably the first one's left-handed? 15%, right? What's the problem? The next one's left-handed.
15%.
15%, and the next one?
15%.
So you guys see how that's really 1/5 to the 3rd power? Of course, right? 15, 15, 50 would be 15 cubed. So if I had picked 8 people, it would just be 0.15 to the 8th power, so forth. What is 0.15 to the 3rd power? Somebody help me out.
0.003.
Say again?
0.003.
0.003. Give me one more number. 003.
3.
7.5.
4.
4?
Yeah.
0.034.
Yes.
Okay. 0.34%. And we expect it to be very small. It's really small chance I'm going to get 1 person, a 50% chance. So to get 3 people randomly that are left-handed should be very small, and it is. So here's what this is really leading up to. Let me see if you guys can see what this means here. The probability I get this. Who knows what that might mean given the context of what we're talking about? Left, right, left. So I love the hangman game because you can fill in the spots exactly as for what I'm asking to put there, right? What do I want to put in the first spot?
15%.
A left-hander, that's 15%. I want a right-hander, or at least not left-handed, right? A right-hander in the middle, what's that then?
85%.
I love it. Where'd that come from? Some of you guys don't, I have no idea where the hell I came from.
15.
The complement, right? If 50% left, must be 85% not left. We'll call them right. Some people call themselves ambidextrous, but pick a hand. So 85. And the last one, of course, I want it to be another left-hander. There's 15 again. I love this idea of just building the group that you want. I want a left-hander here, put the probability. I want a right-hander here, put that probability there, and so forth. Right? You can build up whatever group you want. And what do you get here? Something. I don't know.
0.019. 0.019.
0.019? About?
Yeah.
So almost a 2% chance. It went way up, of course, because the right-hander gives me a big old boost in my probability, right? Yeah.
I have a question.
Yeah.
So you don't divide it by anything?
Do you see how percentages are already divided by something?
Yeah, by 100.
They already are.
You don't know about that then.
Exactly. It's built in.
Okay, that's what I was not confused.
So, for example, I want you to realize something. Let me kind of take this, because here I was dividing by something, and I understand that. What's the probability of a king? 4 to 52. What's that as a decimal? I haven't asked that yet. What's 4 divided by 52?
That is 0.02457.
Point.
0.076.
Oh, what?
Okay, that's something. So about 7.6%, right? So if I want 2 kings.
How did you get 0.0?
I put 4 divided by 52.
Yes.
Oh, okay, I have mine something.
4 divided by 52, right?
Something wrong.
Okay.
I had 15 on mine too.
Okay, 52 definitely cards, right? If I want 2 kings, can I look at that like king, king? What would go here for king? 0.076. What would go here for king?
0.076.
So if they're given to me as a percentage, it's already been divided. The bottom is already in there, right? And that's a mistake somebody made. Remember this mistake here? They said there are 100 people. No. 15 over 100 is 15%, but it's not 100 people. It should be 15% of 310 million. That's the number that should be up top if you want to do it that crazy way. Right? Okay. This, though, is a lot. This makes these kind of problems very simple, believe it or not. So let me do another problem based on that over there. Let's say I want to pick 7 people. And I want the first 3 to be left-handed. And then the next 3 right-handed. And the last one to be left again. That's what I want. For whatever crazy reason. I want to know the probability of this to happen. Right? What would that look like? I can kind of write it out for myself. It'd be left, left, left. Right, 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 left. Anybody got a suggestion before I put numbers up that will make it a lot easier to write the math out? Do you remember here how I had 15, 15, 15, and that was 15 cubed?
15 cubed.
Isn't that L, L, L? Isn't that L cubed already? So how can I write this? This would be L to the 4th, R to the...
Third.
Do you guys get that? I'm just multiplying anyway. Isn't that the reason we took algebra? This is one little reason why we took algebra here, is so you can handle what I just said. It really makes the math a lot easier to get to. This will become very handy when we get to chapter 5 and we start talking about things that have 2 possible outcomes. Right? It'll be yes or no. I want to be able to put those together. Yes?
So for small populations, is the order going to matter? So I know that doesn't matter right now because
the order matters in the sense that, like here, if I said I want a left-hander and then a right-hander and then a left-hander, that's the probability. If I said I want 2 lefties and a righty, that would not be the right answer. Because is that the only way to get 2 lefties and a righty?
No.
Can't you get left, right, left, or left, left, right, or right, left, left? There are more ways to match what I want then. And what does or mean? Or basically means add. So I have to add all those probabilities together. Here this is very specific. It says only this. I just want this. Whereas if I said the probability I get 2 left-handers, there's more than one way to do that. The first 2 could be left-handed, the last 2 could be left-handed, so forth. Yep.
But the probability wouldn't change because you're still multiplying the same thing.
Each one wouldn't change, but you have to add them together to get the answer. So the question was probably of 2 left-handers out of 3. Then it could be LLR, right? What's another way to get 2 left-handers?
RLL.
RLL or LRL. Each one of these would be this. So mathematically, you're right. Whoever asked that question, mathematically, the order doesn't matter because you multiply. Who cares? But the question, if the question says order doesn't matter, there's more ways to match it then. Here, there's only one way. LRL. That's all I want. I want lefty, righty, lefty. Cool. But when we get to chapter 5, they're going to say, I want 2 left-handers out of 3. Oh shit, there's more than one way to do it. I got to get all the ways and add them up. Okay. And that's, again, this is a little bit ahead of us, but I like the question came up now. Yeah.
Yeah, how come you don't put left hand power two left hand power, right? And multiplied by R.
Yeah, you could do L squared R.
Yeah.
And that's what each of them are, right? And how many are there? 3. Cool. Exactly. Yeah.
So for that, you just do one of them and then multiply by
Multiply by
different
3.
ways.
Exactly. I love it. I love it. But again, I'm getting a little ahead of myself, which is good though, because if we could talk about it right now, it's going to make chapter 5 that much easier. As long as this stuff is actually sort of making sense at the moment, which is what I'm hoping. So is this cool? I mean, I want first 3 left-handed, next 3 right-handed, the last one left-handed. So it's L4R3. So what's being raised to the 4th power?
15.
0.15. What's being raised to the 3rd power?
0.85.
And you can read it off. I want 4 left-handers in certain places and 3 right-handers in certain places. That's what that says. 4 of these guys, 3 of those guys. Right? In a certain place. Multiply that out and you got it. So this to the 4th times this to the 3rd equals something. I don't know. Something probably really small. Somebody did that on the calculator?
0.000031.
Woo. Yeah.
I got like e to the negative 4.
That's me.
I like it. So what'd you get? Read it off to me. What'd you get?
I erased it.
3.109007813 e to the negative 4.
Yeah.
All right. That E, and that I thought that might be why you guys are being quiet. You're all like, my calculator just went crazy. No. This E means times 10 to the. Oh shit, there's a whole reason for scientific notation to learn it. I can't believe it. So be careful. Don't tell me the probability is 3. Why am I going to freak when you tell me the probability is 3? Because the highest it could be is 1. You're trying to tell me it's 311% chance. Like, holy crap. So even when you don't mean it to happen, these people will walk into your room. We're here. Oh shit, I didn't even look like. So this E means times 10 to the. So did you see how, of course, it's going to move it back 4 times? So you always put 1 less. In fact, I think I moved it too many times then. I was trying to follow you with how many zeros you were saying.
Yeah, I think I gave you an extra one.
Okay, that makes more sense. Because we'll move it back 4 times, it'd be 1s and then 3 zeros. Right? So be really careful. It's very likely you guys are going to have some problems. They're not going to come out to be positive exponents, because that would be too big. They're going to come out to be negative powers. Very small chance of something happening. Okay. And of course, this makes sense. It'd be a very small chance of randomly getting this. Right? We just pick 7 people, and I get the first 3 left-handed, the next, and that's a very small chance it's going to happen. I love it. Okay. Let me see. One last thing to talk about, and I desperately want to get you working on this, because that's when I can walk around and hit specific issues people have. One last thing to talk about is this. And we're just going to go back to cards, because it just makes it easy. Remind me, what goes on the bottom of a probability always?
Number.
The total number of things it could be, right? So if I pick one card, and I want to know the probability that that card is a king, that's of course 4 to 52. We've done that enough, right? We know that. So that's, I don't tell you a damn thing about it. I just say, what's this card? And you think it might be king, you got that chance to be right. If I let you ask me a question to try to reduce the probabilities a bit, or increase your probability, sorry, that you're right. Let's say you ask me, is it a face card? Right, that might be a good question to ask. Because if it's a face card, what should happen to the probability that it's a king? It should go up. You should have a higher probability. So what's probably it's a king given that it's a face card? So you ask me, I say, okay, here's the card, put your money on it, and you put your money on a king, and then I'll let you ask me a question. So you know if you're going to lose or win, what your probability is. And I say, yes, it is a face card. Yeah, it's a face card. How many cards could it be then?
12.
Why?
So 4 times 3.
Exactly. Isn't there a jack, queen, king in each suit? So how many face cards are there? 4 times 3. There's 12 face cards, right? Jack, queen, king, 4 times over for each suit. How we doing?
We're not.
So let me stop. Face card. Jack,
It should be
queen,
16, shouldn't it?
Jack, queen, king. Are there any other face cards? Any other cards have a face? No. Jack, queen, king of clubs, diamonds, spades, hearts. So how many total cards? 4 times 3 is 12. There are 12 face cards.
4.
Jack, queen, king of hearts.
Okay. I see.
Clubs, yeah. 1, 2, 3, 4. So it's going to be 12 face cards. I like it. So what's going to go on the bottom of this probability then? Careful. What did we just say? Could it be any of the 52 cards if I say yes, it is a face card? It can't be any of the 52 cards. It's got to be one of those face cards, right? I really want you to see, if I give you information, then you can discount some cards. You say, well, it can't be any of those. So if I say, yeah, it's a face card. It could be Jack, it could be Queen, but it might be a King. But it can only be then how many total cards? 12. That's all. You can throw the 7s away, the 2s away, all the number cards away. You can throw them all away. They can't be them. So the bottom, the idea of the bottom never changes. The bottom is always the total number of things that it could be. If I give you information, it could be less things, right? So whenever you see a given, that's going to make the bottom go down. Yes, sir?
Do you count the ace or not?
Ace doesn't have a face. It rhymes, but it doesn't have a face. Right? So that's a jack, a queen, and a king. They can all look at you with 2 or 1 eye, right? But the ace has no face to look at you. Cool. So out of no jack. Out of 12, how many are kings? 4. I like it. This is something called a conditional probability. You can see, based on the condition that it's a face card, that's what the probability becomes. So it goes from 7.6%, right, to 1/3, which is 33.3 repeating percent. Your probability of it being right just went up by almost 5 times, right? 4 times roughly. So let me give you one more example like that. What's the probability it's a king given it's a heart? So then you ask me a question, you say, is it a heart? I say, yes, it's a heart. So now you know it's a heart.
1.
Careful.
1/12.
Careful.
1 over 13.
What do you know about the card? What do you know about the card? It's a heart.
It's a heart.
All right, so probably a king given that it's a heart. How many hearts are there then? 13. Remember, 13 in each suit. How are we doing so far? The bottom is always the total number of cards it could be. So really, if there's a given, it's just how many of these there are, right? That's it. You're given this. Yeah.
Given is mean always gonna be division, right? Division, right?
No. Given doesn't mean division. The symbol for it looks like division, which is unfortunate, but given just means I know this about it. If I don't know a damn thing about the card, 52 goes on the bottom. Why? Because it could be any of those 52 cards. Shit. But if I know it's a heart, it can only be how many cards? 13. There are 13 hearts. Out of those 13 hearts, how many are kings?
1.
So does a 4 go on the top?
1.
4 can't go on the top because I told you it's a heart. So how could it be the king of clubs? How could it be the king of diamonds? So there's 1 king out of those 13 hearts that I know it's a heart. Did my probability just go up from what king was? You sure about that? It was probably a king by itself. 4 to 52, which reduces to 1 out of friggin' 13.
Oh, that's
So that was actually a really stupid question to ask. If you think about it, why does my probability not change? Because I throw out all the clubs, the spades, and the diamonds. But, right, 3 suits, but each one had a king in it. So I threw those kings away too. And I'm trying to get a king, so of course it stays exactly the same. So did it being a heart, knowing that it was a heart, did that change the probability that it was a king? So we would call these two things independent events. And that word is beautiful here. Independent in real life means one thing does not affect the other thing. So a heart happened. Did the king care? No. The probability did not change at all. So I call these independent events. Now I'll tell you what. We're going to go over that more, but I'm trying to get to a point where I want to give you this and start working on this so I can see where our issues are, right? So let me give you this. If you want to, you can work in groups or you can work by yourself. I've got the answer key that I'll give you at the end of class.
Can I ask a question?
Yeah.
For that one, would you leave it like this?
Where are we at?
Would we leave it like this?
Yeah, or you can make it into a decimal. Yeah.
Professor,
Yeah.
is the question is they kind of change the words and it's gonna be the same answer, right? Kind of
Oh,
change the words.
yeah. Whatever. If this happened, given this, but the probability of this didn't change, that's independent. But like over here, our king and a face card, are they independent? No, it changed from 4 to 52 to 4 to 12. So face card affects the probability that that's a king. They affect each other. Okay, good. Just make sure everybody understands this is not a quiz. We work together. I don't even want you to turn this into me unless you have a question about something. I'm going to give you the answer key before you leave. All right, so don't. This is not the quiz yet. This is just practice.